This video is sponsored by DataCamp, an online platform to learn data science. For real integration, there are two kinds of intuition. The most common one is area under a graph. So if the function is f of x, then the area is the integral here. The other intuition is a little more physical, the mass of a long rod, which spans from A to B. This is basically just thinking of f of x as a density function. However, the basic idea behind these two views are the same. It can be thought of as a sum of lots of components. Here, they are areas of rectangular strips. The height is f of x, the function value at that point, and the width is a small increment in x, say dx. So the integral here is just summing up all these f of x dx. I mean, after all, this symbol is just a long s for sum. For the rod intuition, the integral just represents summing up masses of these little rods. F of x represents the density of the rod at that point, and dx is the length of the little rod. We are going to replicate the concept of summing up little things for complex integration. However, this is slightly more complicated. Generalizing the integrand isn't difficult, simply replace it with a complex function. So in our rod intuition, we have to think of the density as a complex function? Weird, but still, roll with it. Next up, we have to change our dx to dz, a complex increment. But what does that even mean? Well, focus on that tiny rod with length dx. In the complex analog, dz would mean a small complex increment, so the length is a complex number now. The final thing to generalize would be the upper and lower limits. The thing is, we can't just let these limits be complex and call it a day. The difference here is that in our previous case for real integration, saying from A to B isn't ambiguous. There can just be one direction to go. However, in the complex world, saying from A to B is not specific enough because we are on a plane now. The straight line path is just one of the options, and you can also have a curved rod from A to B. And the thing is that integrating along different curves could be different, so we have to specify the path taken. So let's denote this curved path to be gamma, and the integral along gamma is denoted like this. This directed path is called a contour. Usually though, we will be dealing with closed loops, and in this case, we can use a fancier integration symbol to say that we are working on a closed contour. But honestly, as long as you specified your curve gamma correctly, the original one is still fine. So that's essentially the definition of complex integration. But the thing is, how do we compute this? I mean, technically, you can just repeat the definition and sum up all the dz contributions, but that's way too inefficient. Well, one slightly better way is to do direct parametrization. It starts off like this. Well, we don't know how to do complex things, but we do know how to integrate real functions, or rather, even if the integrand f of x is complex valued, as long as we are integrating over the reals, we can always just separate f of x into its real and imaginary parts, and integrate each part separately. So, what if, somehow, we can apply another function phi that transforms the real path over to the complex path? Then we can just focus on this familiar setting. The process of finding phi is parametrization, and so now the path is from phi of A to phi of B. We wanted to compute the integral of f of z dz along this contour gamma, and we now want to replicate it in the real setting. So for a given patch of the real world near a point x, we should associate it with f of phi of x, because after the phi transformation, this will be the corresponding function value at that point. The catch is that it is now a complex increment rather than just a real increment in the real case, so we need to scale dx by something to get dz. From the intuition we developed on differentiation, this is precisely the derivative of phi at x. So the complex integral is now represented just as a real integral. To reiterate, by the parametrization, z is simply phi of x, and a small complex increment dz is related to dx by the scaling factor phi prime of x. And this, well, doesn't give us too much insight for now. To have more insights, we need to go to the second chapter. I have mentioned Pólya vector field in those two videos, but a brief recap wouldn't hurt. For every point z on the complex plane, we attach a vector corresponding to the value of f of z, but conjugated. More explicitly, if we write z and f of z in their real and imaginary parts, then the vector to be plotted would be u minus v. I think it might be worth pointing out that both u and v are actually functions of x and y. However, if we directly attach such a vector to even just a selection of z's, the long vectors can clutter up the plot, and so usually we standardize the length of the vectors, and sometimes use colors if we really need to indicate the length. But what is so special about this construction? This will require a few steps of straightforward manipulation, so pause if necessary. First, we will compute the divergence of the resulting vector field, which can be thought of as this, and then we get the difference of partial derivatives. And the 2D curl of the same vector field can be similarly calculated, and this time it is the negative of a sum of these partial derivatives. But if we put the two expressions together, does it ring a bell? They have something to do with the CR equations. More precisely, the first equation is equivalent to saying that the divergence of the Pólya vector field is 0, while the second one is equivalent to saying the 2D curl is 0. To reiterate this, if f satisfies the Cauchy-Riemann equations, the divergence and 2D curl of its Pólya vector field are both 0. Isn't that amazing? However, this field has another use we are going to see right now. Let's go back to complex integration. Just like before, we integrate from a to b through the path gamma, and the integral tells us to sum the contributions by these little complex increments dz. But now, think of the complex number f of z as a vector, and dz as a vector as well, and focus on f of z times dz. To do that, we can consider the arguments of the two complex numbers. Let's say the argument of f of z is alpha, and that of dz is beta. Then multiplying them just means multiplying the modulus and adding up the arguments. How's this gonna help? Well, enter Pólya vector field. The vector attached at this point is f bar with argument negative alpha. But the angle between f bar and dz is special. If we call this angle theta, then it is precisely the difference between the angles beta and negative alpha. And in fact, theta is just alpha plus beta. Let's clean things up for a bit. The only angle we'll be dealing with from now on is theta. By Euler's formula, we can rewrite e to the I theta. Now, does the first term here ring a bell? Multiplying the magnitudes of two vectors and cosine of the angle between them, yes, that's the dot product of the two vectors. So if we think of F bar as the force and dz as the displacement, then this product is simply work done by the force over a small displacement. And so integrating over the contour means the total work done by the Pólya vector field on gamma. That's only the real part of the integral. What about the imaginary part? Even though it screams cross product, we'll use something else. We'll consider the normal to dz. Then angle made between the normal and f bar is pi by 2 minus theta. Since sine theta is just cosine of this angle, we can identify this imaginary part as another dot product. More precisely, it should be the dot product of f bar and the normal. This time, we think of f bar as fluid flow and dot it with the normal to dz, which can be physically interpreted as flux, which means how much fluid is going directly across dz, or basically the component of the fluid velocity normal to dz. With that in mind, after summing up all these contributions, the imaginary part of the integral would be the total flux of fluid across this contour. So just to recap, the complex integral can be made more intuitive. The real part is the work done by the field F bar, and the imaginary part is the flux by the field F bar across gamma. This is an amazing result, because if we have the Pólya vector field, then work and flux are quite tangible things. For example here, the vector field goes across the contour gamma from left to right at basically every point, so without any calculation, we know that the imaginary part is quite positive. But this result has another very important consequence, which is Cauchy's theorem. Proving the theorem is now just combining results we know. We now suppose gamma is a closed contour and the region it encloses is D. Then Green's theorem says the line integral around gamma is related to the area integral of the 2D curl. But the left-hand side is work done along the closed contour. Next up, we have divergence theorem, which relates the divergence integral to an integral across gamma, and the left-hand side is flux across the closed loop gamma. Finally, we know from a few minutes ago that the divergence and 2D curl of the Pólya vector field are both 0, as long as f satisfies the Cauchy-Riemann equations. So let's combine all these results together. If the CR equations are satisfied everywhere in D with continuous partial derivatives, then both total work done along and total flux across gamma are 0. Since the complex integral can be written in terms of work and flux, it will be 0. This theorem is so important that I think we need to get it right. Let's say both gamma and D live inside a bigger set U, and F is holomorphic or complex differentiable throughout this bigger set U, and gamma is any closed loop completely inside U. Then the integral of F around gamma is 0. This is actually not precise enough, and here is just a glimpse of how we make things rigorous. Don't be intimidated by the maths jargon, I just want to get a point across, so bear with this bit. One version of this theorem is to require U to be a simply connected domain. Essentially, this means that any closed loop like this one, gamma, can be continuously shrunk to a single point. If I remove a point here, say this white dot, then we can't shrink it all the way to a point. So in this case, u minus a point is not simply connected. The other, more general version only requires that u is open, but gamma is what's called homologous to 0. To put it more simply, this means that for any point outside of u, the winding number of gamma about that point is 0. In both versions of the theorem, we require that the curve gamma is piecewise smooth. Anyway, the point is that the derivation is only the big picture, and I have swept a lot of assumptions under the rug. Still, it is very important to see the big picture first and care about those little details later. But why is this theorem so important? It feels like this trivializes complex analysis because the integral is always 0. But first, f needs to be holomorphic throughout the set U, so if f is not holomorphic, even just at the point, this theorem fails. In fact, we are going to compute the integral of 1 over z later, and 1 over z is not holomorphic at 0, at least on the traditional complex plane. So why is this important? You have just told me that sometimes it doesn't work. Well, let's say that the region where f is holomorphic does not completely cover gamma and d. Suppose that we integrate anti-clockwise along gamma, then another slightly modified curve will give the same value for the integral. Why? Well, if we reverse direction in one of those sections, then applying this theorem, the integral would be 0. More specifically, the integrals along the different sections add up to 0, and so they are negative of each other, but the negative sign can be cancelled by reversing the direction we integrate along, and so these contours would give us the same integral. So as long as f is holomorphic in the region between two loops, and the two loops are both anticlockwise or both clockwise, the integrals remain the same, which allows us to deform the contours, and very useful sometimes. And like I said before, we are going to deal with 1 over z now, using the ideas we have just seen. But before that, I want to give thanks to this video's sponsor, DataCamp. DataCamp is an online learning platform that offers more than 350 different courses for you to learn basic and intermediate Python, SQL, and R, and how to visualize data using those languages. I am personally going through the Introduction to R course because I didn't have the chance to learn R before, and this course is very friendly to beginners. You might notice that there is XP points here, and this is what I really like. Even if you get the wrong answers, it wouldn't affect your XP, but you will earn less XP if you take a hint. Rather than being spoon-fed, it encourages you to actually try, which is very important in learning a new skill. Data science is very useful in any field of work these days, and you can use my link in the description box below and check out the first chapter of any DataCamp course for free. Now, back to the video. In this chapter, we will focus on integrating 1 over z around a closed loop gamma, and gamma is a circle centered at the origin with radius r, and we integrate anti-clockwise. But before we actually compute it, it's good to have a rough idea of what we should expect. This is the Pólya vector field for the function 1 over z. Based on our previous chapters, we know how to get the complex integral from this vector field. The real part is the work done by this field along our contour. However, our field is perpendicular to the contour, and it happens everywhere along the contour, so we should expect the total work done to be 0. What about the flux? Well, this time the field goes from left to right, so we experience positive flux. And this left to right is everywhere along the contour, so we should expect the flux to be positive. So without any computation at all, we already know that the integral needs to be purely imaginary, and the imaginary part is positive. But how to calculate the exact value? Well, here is one way to do it. We will be using the direct parametrization method. To use it, we need to know what the parametrization phi is. The most natural way to parameterize is through the argument. So 0 would correspond to the point on the real axis here, and going from 0 to 2 pi corresponds to going around gamma once. To make this a lot more explicit, we need the formula of phi. In this case, phi of x is r times e to the ix. Well, actually, because we are working with angles, it makes a lot more sense to declare the variable theta instead. And now, it is a matter of plugging stuff in. We have the formula of phi, and also the lower and upper limits being 0 and 2 pi. And just plug stuff in and use the formula here. Note that the denominator here is phi of theta, and the function f is 1 over z, so we have this first part, and the remaining bit is just the derivative of phi. But we can clear denominator entirely, and we are just left with I in the integrand, and so the integral turns out to be 2 pi I. It is worth noting that the value of the integral does not depend on r, even though the contour gamma depends on r. This is because even if we have a different radius, f is holomorphic in this pink region that encloses the region between two loops entirely. So by Cauchy's theorem, the two integrals are the same. So in this chapter, we see that the integral of 1 over z around a circular contour is 2 pi I, and it is also nice to realize that the contour is traversed anti-clockwise. And this integral right there, I would say, the most important integral throughout complex analysis. For the next chapter, we are going to look at more integrals. Similarly, we think of the integral of 1 over z squared. Just like the previous case, the radius r doesn't matter, as long as it encircles the origin. And again, we'll use the work flux result to get some rough idea first. This is the Pólya vector field of 1 over z squared, and let's see how it helps. First, let's see the work done. Well, for the upper half of the loop, we can see that the vector field generally aligns with the direction of travel, and so the work done on the upper half is positive. But on the lower half, the vector field generally works against our direction, and so the work done on the lower half is negative. And due to the up-down symmetry of this vector field, the overall effect is that no work is done along gamma. What about the flux then? This time, we first focus on the right half of the contour. The vector field generally points out of the loop, and so the flux on the right half is positive. And on the left half of the loop, it generally points into the loop, and so the flux here would be negative. So just like before, we can use the left-right symmetry of the vector field to conclude that the overall flux across the loop should be 0. So the integral turns out to be 0. But what about 1 over z cubed? Of course, we can consider its Pólya vector field, and by symmetry this would be 0 again, but is there a more general way to do it? Consider instead a field which is a superposition of a source field, which can be thought of as a copy of 1 over z, like what we saw before, just translated. On the other side, we have the opposite of a source, so we call it a sink. And this is a copy of negative 1 over z, again translated. If we bring these together while doing the appropriate scaling, we should get the vector field of 1 over z squared. How does this help? Well, let's revert back to the source and sink separated. We now try to integrate along a large closed loop enclosing both the source and sink, and we'll deform this loop, which means we consider this loop instead. Again, the integral along this loop will be the same as that on the original loop, because it encloses the source and sink together anti-clockwise. Not too surprisingly, these two circular loops would give exact opposite values, and so they cancel out each other. And for the link between them, the overall effect is just going back and forth, and so the integrals would again cancel out each other. So the integral along the original contour would be 0, and this has nothing to do with the distance between the source and the sink. So throughout the process, the integral along this loop is 0, and hence at the end, the integral of 1 over z squared is 0. This can actually generalize. This time, we put these two opposite fields together. On the right, we have a 1 over z squared field translated, and on the left, similarly, we have a negative 1 over z squared field translated. And again, we try to merge these two fields together, scaling appropriately, and in the end, we get a 1 over z cubed field. And so, using pretty much the same argument as before, we can conclude that again, the integral is 0. And then using the same argument, the integral of 1 over z to the power 4 would be 0 again, and so on. If you are wondering why combining the opposite fields of 1 over z would give 1 over z squared, or combining opposite 1 over z squareds would give 1 over z cubed, you can pause and verify this limit over here for n larger than 1. These two are the opposite fields that we have been doing, and this prefactor here is the appropriate scaling that I was talking about. In fact, this limit is pretty much just the derivative of the negative powers of z. Anyway, in summary, for gamma being a closed loop around the origin, first off, the integral of 1 over z is 2 pi I, which is, as I said before, the most important integral. Next, we have the integral of 1 over z to the n is 0 as long as n is larger than 1. This is what we have spent this entire chapter on. And if we have positive powers instead, then the integral is 0. This is because the function will be holomorphic and we have Cauchy's theorem. So among all the integer powers of z, the integral is 0 except for 1 over z, which is partly why this is so important. You might see where this is going, but we will take a look at Cauchy integral formula first. This time, we are going to investigate this type of integral, where gamma is any closed loop around A, and f is any function holomorphic throughout the region enclosed by gamma. Calculating this integral is not too difficult if we first try to deform this loop. The thing about this integral is that f of z is holomorphic within gamma, and so the integrand is holomorphic except possibly at A. So by Cauchy's theorem, we can just shrink it very close to A, and the integral remains unchanged. The advantage of doing this shrinking is that now every point on this loop has its function value very close to f of a, and so the integral can be estimated by replacing the numerator as f of a. The good thing here is that f of a is a constant, and so it can be taken outside of the integral, and what remains in the integral is a disguise of the integral of 1 over z, just translated by a, and so it is 2 pi I. Now, the approximation sign would be an equal sign when we shrink the loop further and further towards A, and so this is really an equality. So, by a rearrangement, we have established this equation, the Cauchy integral formula. However, what is so special about this formula? The first thing to notice is that since we are integrating along gamma, we actually only need to know the value of f on that path, and yet we are able to determine the value of f in the interior of gamma. Actually, every point in the interior. This just demonstrates how rigid holomorphic functions actually are. The other consequence of this formula, relevant to what is coming next, would be to differentiate it. Here is what happens when you try to differentiate with respect to A. Here, I'm just differentiating the 1 over z minus a part. Now repeat this trick and differentiate. Again, I'm just differentiating the 1 over z minus a squared part, but just note that there is now a factor of 2 here. And we can keep going, and in general, this is the formula for the nth derivative of f. There are two messages in this more general form of Cauchy integral formula. From a more theoretical perspective, this tells us that we can differentiate any holomorphic function however many times we want. From a more practical perspective, this is one way to compute the derivative of f using just the value of f on gamma. And now we go to the most useful theorem of complex analysis, residue theorem. Residue theorem is a general method of computing the integral of f of z around a closed loop. Now, f of z would not be fully holomorphic, otherwise we know this is 0 by Cauchy's theorem. However, for residue theorem to work, there can only be a finite number of points where f is not holomorphic. These points are usually called singularities. Just as we have done before, we are going to deform the loop to our advantage. This is the loop, which might look complicated, but this blue dot will track the path for us. First off, it tracks anti-clockwise around one of the singularities, then it goes to another loop, and from there tracks anti-clockwise around that singularity, and then repeats for another singularity, ultimately back to the original spot. Now the good thing here is that the integral around this triangular loop should be 0, again by Cauchy's theorem, and so we can just focus on those singularities. But still, how do we compute the integral around those singularities? We have actually calculated easy examples of integrals before using integer powers of z, so an idea would be to break down f of z in terms of these integer powers. If this is possible, then all the terms involving negative powers of z except -1 would give 0 contribution to the integral. And of course, all the non-negative powers of z would give 0 as well. And then we are just left with the -1 power term. And so, integrating f of z would be 2 pi I times that -1 power coefficient, where gamma here is just a closed loop around A, and the 2 pi I is that most important integral. But can we actually express f of z in this series? After all, if that's not possible, these discussions are useless. But good news, we can. This is called Laurent series, and for the purposes of integration, the most important term would be the coefficient labeled c-1 here. And so we give it a name, residue at A. Now, technically, Laurent series requires some assumptions to exist. If this is A, where the series is centered around, we need f to be holomorphic in an annulus around A. But this assumption is pretty much always satisfied for our purposes. Anyway, the most important takeaway here is that the integral of f of z around a is 2 pi I times the residue of f at a. There are many ways of denoting this, but I'm going to use this notation, res sub f of a. And if we go back to the integral we are working on, labeling the singularities, then the A1 loop contributes 2 pi I times the residue there, similar for the other singularities. And so, the integral of f of z would simply be 2 pi I times the sum of the residues at the singularities that gamma encircles. But I think it is important to point out that gamma, just like here, needs to be traversed anti-clockwise, and ta-da! This is the residue theorem. But how do we actually compute those residues? It turns out that a lot of the time, just doing a series expansion and extracting that -1 power is the most efficient method. So for example, if we need to find the residue of e to the 1 over z at 0, then from the usual power series for the exponentials, we can just directly substitute 1 over z there, and the residue would be 1, because that's the coefficient of 1 over z here. From the famous book Surely You're Joking, Mr. Feynman, one time Feynman boasted, I can do by other methods any integral anybody else needs contour integration to do. So Paul puts up this tremendous damn integral he had obtained by starting out with a complex function that he knew the answer to, taking out the real part of it and leaving only the complex part. He had unwrapped it, so it was only possible by contour integration. He was always deflating me like that. He was a very smart fellow. Here, he was talking about real integrals, yet those are only possible by contour integration. Now, nobody actually knows which integral he is talking about, but there is a nice thread on Stack Exchange that tries to create one anyway. The idea behind is not actually difficult, just using Cauchy's integral formula, but it creates really scary looking integrals which could definitely have stumped Feynman. But there can be some other real integrals that are easier to compute using complex analysis. One standard example is this integral, but I will skip through the details of calculation here because I want you to do it yourself. To convert it to a contour integral, the most natural choice of the integrand would be to simply replace x by z, but it turns out that integrating cosine is usually bad in complex settings, just from experience, and so we use e to the iz instead and take the real part. In this case, however, they are equal, where the path gamma 1 is the real line. Can you figure out why the imaginary part of the integral would automatically be 0? To harness the power of complex analysis, we first consider the finite case where the path goes from -r to r, and then close the contour by going on a semicircular path anti-clockwise from r back to -r. The integrand is not completely holomorphic, and the singularities are precisely plus and minus I, because they make the denominator 0. The closed contour encloses exactly one of those singularities, namely I. By residue theorem, the integrals along two parts of the contour add up to 2 pi I times the residue at I. The straight line part is exactly what we want when r tends to infinity, and the residue is something that can be readily calculated, so we hope that this semicircular part is easy. As it turns out, in this specific case, this goes to 0 as r tends to infinity, and so we only need to calculate the residue here. So the details that are left would be why this will tend to 0 as r tends to infinity, and how to calculate the residue in the first place. I have considered going into more details, but to be honest, I don't really know how many people will watch until this point, so if you're still here, leave a comment. Basically, to preserve my sanity in making a 30-minute video, I have put some links in the description for the details required instead. Hopefully, this basic idea is still fascinating and actually just the core of the whole thing. If you're still watching, please subscribe with notifications on, like the video, comment, and share the video as well. See you next time. Bye.